Today we shall be interested in understanding what we have been discussing since the last class, the notion of pressure from the kinetic theory of gases. Now, in the last class we discussed how we perceive sound. So, if we consider that the air around us is composed of molecules, then clearly these molecules, as they bombard our eardrum, it should result in this discrete clicks, but we don't feel those clicks. We get some kind of an averaged effect which we perceive as sound. So, what is this averaging and how do we conceive sound or any kind of pressure is something that we will study today. Okay, so the actual dynamics of molecules of a gas is extremely complicated, as you can understand, because these molecules are not only moving around, they are colliding, and the nature of intermolecular forces is rather complicated. But we shall not go into all the details. We shall not even care about the fact that these molecules have internal structure and there are electrons and protons and there is some kind of quantum mechanical phenomena going on at the small distance level. So, we shall approximate the actual picture of a gas by what is called the kinetic theory of gases, whereby we shall treat these molecules essentially as hard spheres. So, they are like billiard balls and they are colliding elastically. So, there is no loss of energy during collisions. Secondly, we will also assume that there are no intermolecular forces, again a raving approximation, because that is clearly not the case. So, we will ignore any intermolecular forces. We will also ignore the fact that there is a possibility of the velocity of the particle changing as it travels between two collisions. So, we will assume that the only point when the velocity of the particle can change is during a collision. So, and these particles essentially travel in straight lines. So, with these simplifying assumptions and assuming that the molecules of a gas are in constant random motion with speeds ranging from very small values to very high values with a distribution of speeds, we are going to try to understand the nature of pressure from the microscopic perspective. Okay. So, let us consider for this purpose a box. So, we set up our coordinate system and we consider a box and inside this box we have the molecules which are moving in all directions with all sorts of velocities. So, typically we will denote the velocity of a particle with this symbol V, which is Vxi plus Vyj plus Vzk. And as I said, since any velocity is possible from very small to very high values, there will be a distribution of velocities. All right. Now, how do we perceive pressure? So, if we consider one of these surfaces, one of these faces of the box, then constantly we have these particles bombarding on the surface, and as a result of which it imparts, each molecule would impart momentum. So, there is a momentum that is imparted to the wall every time there is a hit. And if there is a momentum transfer in the form of an impulse, there is going to be a force felt. So, if you assume that this surface was free and there is vacuum on this side, because of this force it would try to move. Now, you would have to exert a force from outside to keep it in place, and an average effect arising due to many such bombardments would lead to you having to press this with some average force, and this force per unit area would be the pressure. So, this is what is really happening. So, let us consider just one molecule, one single molecule, and let us say that m is a mass of the molecule, and we will assume that all the molecules have the same mass. So, this is a constant. All right, and the total number of molecules is n, so this is the total number. And the volume under consideration is V, so that's the volume. And we can consider an average number density n, which is capital N by V. So these are some basic definitions. Okay, so now let's try to compute the momentum transferred to the wall. So if the particle is moving with a velocity v, then it has a momentum mv, and this v is now towards this direction, so I call it vx. And then as it hits the wall and the collision is elastic and it rebounces back, the total change of momentum will be 2px, 2mvx, sorry. So this is delta p x for a single collision. Now this is for a single collision, so we need to compute the total number of collisions that is happening. So how do I compute that? So if we consider this surface that we are interested in, and assuming that this surface has area A and these particles are hitting it from this side, in the x direction, if you want to compute the total number of particles that are hitting it in time, say delta t, with a velocity vx, we basically need to calculate the number of molecules that are contained in this imaginary region, which has this length equals to vx times delta t, and of course the area is A. So the volume of that region would be vx delta t times A, that's delta v. This v should not be confused with the velocity, this is the volume, and this times the number density, so I put it n, which is capital N by V, is the number of times these particles would hit, because those many particles would actually reach this surface in time delta t, moving with velocity vx along the positive x direction. So then for all of these we have to multiply delta px by that number, and what shall we have? We shall have vx delta t A n multiplied by twice m another vx, so vx square. So this is the total momentum imparted to the wall in time dt by particles moving with velocity vx towards the x direction. Now if I divide this by the time, I should be getting the force, and if I divide it by the area, I should be getting the pressure. But there are two problems here. One is the fact that I have only considered particles moving with velocity vx. There are particles moving with all sorts of velocities. This is just a representative velocity. So I should be using, instead of vx square, the average, vx square average for all the particles. And the fact that I have considered this imaginary surface, this factor of 2 should also disappear, for the simple reason that only half this number divided by 2, half the number would actually be traveling to the right side on an average. Half the number would be moving to the left on the average, so we should actually divide it by 2. So finally we have this expression. So when you divide, dt goes, A also goes, and you have the pressure as m n vx square average. So this is the expression for pressure. Now we have only considered the x direction, but the velocities are moving in all, or are directed towards all the directions. So you have v square, which is vx square plus vy square plus vz square, and we are interested in the average of vx square. So if we take the average of v square, this is equals to average of vx square plus average of vy square plus average of vz square. Now there is no reason to believe why x, y and z, the velocity averages should be any different, because there is nothing unique about the x direction. So x, y, z directions are all equivalent directions. So these three average quantities should be equal. So I can in principle assume, and this is of course a right assumption, that vx square average is same as vy square average equals to vz square average. On an average, this should be the same. So once we have this, you can clearly write vx square average as 1/3 v square average. And the moment you write that, you have this, so that becomes P equals to 1/3 mn v square average. A very, very famous expression, and you can clearly see what the pressure now depends on. The pressure depends on the mean of the squares of the velocities of the particles. So it's mean square velocity that it depends on. It of course depends on the mass of the individual particle and the number density. So if you have a gas with a higher number density of particles, clearly pressure would be high. And of course if you raise the speeds of the particles by some means, again the pressure would be high. So there, of course the mass of the molecules you can think is something which you can't change, but you can clearly see that for a given gas you can play with these two parameters and you can suitably change pressure. So a dilute gas where n is small corresponds to low pressure, whereas a gas where there is a large number of particles will have large value of n and the pressure will be high. So this is the famous expression for the pressure of a gas, assuming the postulates of kinetic theory, and it's directly proportional to the velocity square, average velocity square. Let me raise this up too. Now if I just try to study this expression, we have P and we can write this little n as n by v, then there is m and there is v square average. So if I take this v to the right hand side, we have PV equals 1/3 m n v square bar. Now this mv square reminds us of the kinetic energy, but that would require an additional factor of half, so we multiply this by a factor of half and then compensate it by a 2, so that gives us 2/3 n, and this is just half m v square average. This quantity within parenthesis is clearly what we can now look as the average kinetic energy of the molecules. M is a constant, so you can just take this average on top. So what you have is PV equals to 2/3 capital N average energy. This symbol is often used to denote average quantities. So average kinetic energy. Now in thermodynamics, we have no idea about the internal dynamics of the molecules. There is no way we can say anything about these quantities like V square average and things like that. Neither can we talk about how this average is going to be computed in traditional thermodynamics. But these two are measurable quantities, pressure and volume. These are macroscopic quantities and they can be measured in experiments, and we have a very powerful empirical result which goes by the name of the famous gas law, the combination of Charles' law and Boyle's law. These are empirical facts, and we know that PV is basically proportional to something that we call the temperature. This is empirical, experimental. So we can immediately see that this average kinetic energy must be somehow related to temperature, otherwise these two pictures would be incompatible. So remember, we were saying that if there is one set of laws governing the physics at the microscopic scale and there is another set of laws governing the how nature behaves at the macroscopic scale, they better be consistent. So consistency would demand that this average energy has to be somehow related to the temperature. Now we can simply do it by taking this average energy to be 3/2 times some constant T. So if I actually make this as an assumption where K is some universal constant, it turns out to be the Boltzmann constant, then using this and this, you immediately have PV equals to NKT, where N is now the total number of molecules. Now this is exactly what the gas laws give us. Sometimes instead of the total number of molecules, what it is written as is in terms of the number of moles. So you divide it by the number of moles, and thereby you have number of moles, and you have KT, and this quantity is called R. This N by Nk by N mole. So this quantity becomes R. So you have PV equals to nRT. So what we have achieved through this exercise is the fact that we have first of all gotten an expression for the pressure which we believe is a macroscopic quantity in terms of an average over something which has got to do with the molecular speeds. So we have connected the microscopic description with the macroscopic via this averaging, and then we have also seen that if we believe in this empirical experimental law PV equals to nRT, then the average kinetic energy of the molecules must be proportional to temperature. So both of these are profound statements. Temperature is clearly related to the average kinetic energy, and we have also seen how to relate pressure to the molecular velocities. The important question, however, is how do we compute this average velocity? The range of velocities, the range of speeds that the molecules can have is very wide. The speeds can be very small, the speeds can be very high, and there's a whole range. So the question is, how do I compute this quantity? This is an average. To compute this average, we would like to know the distribution of molecular velocities. So we need to know the distribution of molecular speeds if we know the distribution, which means that we know how many molecules has a velocity v. If we know that distribution, then we can compute this average. But I ask you this question, does it make any sense to say v equals to say 20.378 meters per second? And if I ask you this question, how many particles has this velocity? Is this a good question? See, velocity is a continuous variable, so it is not appropriate to talk in terms of single value of velocity. When you will do probability and statistics, you will see that for continuous variables you can always define something called a probability density instead of a probability. So what we are going to state is this question: how many particles are there with speed in the range v and v plus dv. This is a question which is something we can ask, and this quantity, this question has an answer, and that is what is called the distribution function. So the number of particles with speeds in the range v and v plus dv is called the distribution function. And it's denoted as dnv. So dnv is this, the number of particles equals to number of particles with speeds in the range v and v plus dv. Now, the range of velocities go from 0 to infinity. Well, infinity because we are still not considering relativity, so the speeds could all the way go to infinity. Of course, you don't expect any particle to have that speed, but mathematically you can think of it that it's very high speed. So what you expect is that since this is the number of particles in this speed range, you should actually expect that the integral of dv dnv for all velocities, this should be equal to the total number of particles. Which is equals to n. So one restriction on the distribution function is that this integral has to be the total number. Now, Maxwell-Boltzmann gave the distribution for molecular speeds in the form of a function. We shall not go into the derivation of that because it would require some statistical mechanics, but we can make some statements about the nature of the distribution function. So what we are interested is in this function. So if you plot the speed in the x-axis and you have number in the y-axis, number of particles in some speed range, so you divide this into these little bins and then you basically construct histograms. So the area of this histogram is going to give you the number of particles with speed between this point and this point v to v plus dv, and then you can compute, you can find these histograms and in the limit of this delta v tending to 0, what you have is some sort of a continuous function which we call the distribution function. Now you can already see from the nature of the graph that I have drawn that this is the most plausible situation. You would have a small number of particles with very small speed, a very small number of particles with very high speed, and there would be a large number of particles with intermediate speed. So this is a bell-shaped distribution that you would expect. Now clearly the mean square, V square average, this quantity which determines also the temperature of the gas, if it is high, it would mean that the temperature is high, and when the temperature is high, you would expect that this peak, in which direction would you expect this peak to move when the temperature of the gas is high? It should move towards higher velocities. So when temperature is high, so this is the speed most probable because it has the highest, so it's a most probable speed, highest probability or highest number density, most probable. So the most probable speed, so this is say T1, this is say T2, and T2 is clearly greater than T1. So as the temperature rises, the most probable speed would go towards the higher side of the spectrum. That's one of the things. Let's study a few more things about the distribution function. For example, I give you an example where the distribution function, this d and v, is some constant times velocity. If this is how it is, my question is this a good candidate? So if you plot it, you will see that this just goes linearly, and my question is this a good candidate for distribution function for molecular speeds? Answer is clearly no, because this is unbounded and it's just going up, which means at higher and higher velocity, higher and higher speeds, you would have more and more number of particles, which is of course not seen, that's not expected. So you would expect this thing to go down, and there should be a central peak region and the function should fall off on both sides. Alright, so there is a problem that I have put on the slides, so please have a look at that problem, and we shall discuss that before we get into a discussion of temperature in the next class. So we shall adopt now the thermodynamic approach, the approach of classical thermodynamics, where we shall not be interested in looking at temperature from the molecular point of view, but from the macroscopic perspective of equilibrium, and we'll discuss how to understand and measure temperature from thermodynamics. So that's next class. Thank you.